Hey guys, so let's have a look at this question. You have a particle of charge q and mass m, which is being suspended from a point on the wall by a rigid massless rod whose length is 3 meters. So above this point of suspension, you have another particle of charge minus q, and that's at a distance of L from the point of suspension. So it's being mentioned that on displacing this particle slightly from the mean position, this will execute simple harmonic motion. We'll have to calculate what the time period of that simple harmonic motion is, right? So one more question once again based on SHM in Coulomb's law, right? So the approach is going to be straightforward once again. For all these SHM based questions, we'll have to arrive at the equation either A is equal to omega squared x or alpha is equal to omega squared theta. Right. And since we know that this is going to be an angular SHM case, we'll have to try to arrive at the equation alpha is equal to omega squared theta. So that's the idea we'll try to apply in this question right now, right? So I've already drawn the diagram for this scenario. So let me displace this particle by an angle theta from the equilibrium position. So when this particle is displaced by an angle theta, there are three forces acting on it: tension, mg, and your attractive force. Here you have a minus q and plus q, so you'll have an attractive force acting this way, right? So our aim will be now to calculate what will be the net torque acting on this particle, and we'll try to get that net torque to be proportional to theta, and we'll also get your alpha to be proportional to theta. This is the approach we'll try to implement in this case, right? So let's try to calculate net torque in this case. So you'll have torque due to three forces, that is torque due to tension plus torque due to mg plus torque due to your attractive force. Okay, so what will be your torque due to tension? That will be equal to 0. Torque due to mg over here will be equal to, so this angle over here will be equal to theta. So your component of mg perpendicular to r bar will be equal to mg sine theta. So torque due to mg will become equal to mgl sine theta, right? And what about your torque due to f? Your torque due to f will be equal to, so this angle is 180 minus theta. Since this length and this length are equal, both these angles will be equal to theta by 2. So component of f perpendicular to the rod will be equal to f sine of theta by 2. So your torque due to force F will be equal to F sine of FL into sine of theta by 2. But that will be in the opposite direction. The torque it provides will be in the opposite direction. So your net torque over here will be equal to MGL sine theta minus FL sine theta by 2, right? Here it's mentioned that we have to consider this to be, a small displacement. So we can consider our angle theta to be small. So we'll get a net torque to be equal to MGL minus FL by 2 into theta, right? So we already have arrived at one condition, that is net torque is proportional to theta. So from this now it's straightforward. We'll try to find out alpha. Alpha will be equal to mg minus f by 2 into L into theta divided by moment of inertia. And moment of inertia in this case is you only have a single particle of mass m, so moment of inertia here will be equal to ml squared, right? So this term will now be our omega squared. So now we need to calculate what omega squared is, and from that we can get time period. Time period will be equal to 2 pi by omega, right? So performing the calculation, so omega squared in this case was equal to mg minus f by 2 divided by ml squared into L. So 1L gets cancelled, so this becomes equal to mg minus f by 2 divided by ml. So this is our omega squared value. So mg is known. We'll now have to calculate what f will be equal to. So f will be equal to kq squared by r squared, where r was, so drawing a rough diagram over here once again, where r was the distance between these two charged particles. This was a minus q, this was a plus q. The distance between these two is what we are considering as r, right? And this length is L, this length is L. We know this angle is 180 minus theta, so this was theta by 2, and this was also theta by 2. So once again we'll make use of properties of triangle to calculate what this r will be equal to, right? So I can write r by sine of 180 minus theta is equal to L by sine of theta by 2. So your r from this case will turn out to be L sine theta by sine of theta by 2. So that will be equal to 2L cos of theta by 2. But because theta is small over here, we can assume r to be equal to 2L itself, right? So our force expression in this case just becomes equal to kq squared by 4L squared. And in this question, he's asking us to assume kq squared to be equal to 2mg into L squared. So making use of that assumption, your F will be equal to 2mg into L squared divided by 4L squared. So basically the value of F becomes equal to mg by 2 itself, right? Okay, so now finding out the value of omega squared. So value of omega squared then will turn out to be mg minus F by 2, so mg by 4 divided by m into L. So omega squared becomes equal to 3g by 4L. And once we know omega, we can find out time period. So time period will be equal to 2 pi by omega, which is equal to 2 pi under root of 4L by 3g. Length is given as 3 meters, so 4 into 3. And here g value is asked to, we can assume g value to be pi squared according to this question. So pi and pi squared gets cancelled over here, 3 and 3 gets cancelled. So we'll get our answer to be 2 root 4, which is equal to nothing but 4 seconds. So hopefully the solution for this made sense. See you guys in the next lecture.